So having written our Lagrangian for our two-particle central force problem, we can now go to attack the equations of motion. And as we'll find, the problem will actually reduce to a one-dimensional problem. And we'll see that actually in sections 8.4. We'll build up to that solution in this section. First thing we need to address is the coordinate system that we're going to use. In fact, we're going to set our coordinate system to sit at the center of mass. So we're going to measure everything relative to the center of mass because it turns out that's an inertial coordinate system. Remember that our position of our center of mass can be written like this. So there's a capital x, y, and z. These are the x, y, and z coordinates of the center of mass. Our Lagrangian, remember, we wrote as this. And you can see that there is no explicit dependence of the Lagrangian on the position of the center of mass coordinate. In other words, if we were to just consider the x-coordinate, say, of the center of mass, and apply the Euler-Lagrange equation, we find that the time derivative of the partial of the Lagrangian with respect to x dot, well, that's just going to be mx double dot. So in other words, the x component of the acceleration of the center of mass through the Euler-Lagrange equation, that has to be equal to the partial of the Lagrangian with respect to the x-coordinate, and that's 0. And so what that means is that x double dot is 0, and so x dot is a constant. In other words, the velocity vector for the center of mass is a constant. And so then it represents an inertial frame. And so that we can represent the positions of our two masses m1 and m2 relative to the center of mass frame. And so we'll take that to be our origin of our coordinate system. If we set the origin of the coordinate system to be at the center of mass, that means that we can ignore r dot. In other words, r dot as measured relative to the center of mass is, of course, by definition 0. And so we can ignore this first term in the Lagrangian and only worry about the second term when we do the dynamical analysis. Okay, as it turns out, we get a nice simplification by recognizing the fact that the angular momentum for the system is a constant. Here's our angular momentum expression. We can see that there's the angular momentum having to do with motion of mass r1, and then angular momentum having to do with motion of mass m2. Remember that we're measuring all of our positions relative to the center of mass, and so a little diagram here shows what that looks like. R1, remember, as measured relative to the center of mass, that's given by this expression, and then R2 is given by this expression. Keep in mind there's a little minus sign here. So we can recalculate the total angular momentum for the system in this way. So here's the angular momentum having to do with motion of mass 1. Here's the angular momentum having to do with motion of mass 2. And you can see that each of these terms involves the cross product between an r vector and an r dot vector. And so we can simplify things. We can grab this term, which appears twice in the first expression, so that's here, that's that term squared. We get 2 of these guys in the second line, so that comes into here. And then we're left with mass 1 being multiplied by r crossed into r vector dot, and then you've got m2 being multiplied by vector r into vector r dot. And it turns out again that this combination of masses gives us the mass m1, m2 over capital M times the sum of the masses over the total mass, which are kind of as just 1, and all of that's going to be times r vector dot. And in other words, the total angular momentum for the system is going to turn out to be just r vector times the reduced mass mu times r dot vector. And now because there are no external forces in the system, the total angular momentum of the system has to remain a constant. The conservation of angular momentum for this problem actually means that the motion is confined to a plane. So remember that the angular momentum vector is given by this cross product here. And since the angular momentum vector is a constant and is the result of a cross product between these two vectors, the angular momentum vector will point at a right angle to the two vectors r and r dot. Now, in order for the angular momentum vector to remain a constant as required for this problem, that means that r and r dot vectors will form a plane that is perpendicular to the angular momentum vector. and the velocity vector can never point out of the plane. Otherwise, the cross product with r would change direction. In other words, the angular momentum would not be a constant, but it must be a constant. And therefore, the motion of these two particles is confined to a plane. That reduces the dimensionality of the problem from 3 to 2, so now we just need to keep track of motion in this plane. Okay, so we have a two-dimensional problem now. Here's our Lagrangian, remember, that we're interested in. We can either describe our vector in terms of x and y coordinates, or, as it turns out, a more natural coordinate system to take is the polar coordinate system, r and phi. So r vector dot squared is going to be r dot squared, so that's radial motion of one particle toward the other plus r squared phi dot squared, and so that's going to be tangential motion of one particle around the other. And so that gives us our Lagrangian for this system. Okay, so again, writing our Lagrangian, we have, in terms of r and phi, we get r dot squared, a term there, that's the radial velocity of the two particles moving toward or away from one another. And then there's r squared phi dot squared, this is the tangential velocity of the particles revolving around one another. And then of course we have our angular momentum, our potential energy function, which remember only depends upon r. Now we apply our Euler-Lagrange equation to the phi coordinate. We find that the time derivative of the generalized momentum for phi, well, that's given by this. So here's the time derivative of the generalized momentum for phi. Lagrangian does not depend on the coordinate phi at all. Therefore, this term right here is a constant. So mu r squared phi dot, that's a constant. And it turns out that that's actually a constant, which is the angular momentum for the system. So mu r squared phi dot, that is just the angular momentum for the system, and that is a constant. Okay, so applying our Euler-Lagrange equation to the r coordinate, first calculate the r partial derivative of the Lagrangian. We get two terms. One, that comes from the tangential velocity term in the kinetic energy. Okay, so this actually comes from the kinetic energy itself because there's an r dependence there, so let's not forget that. And then of course we have the negative r partial derivative of the potential energy function. The other term in the Euler-Lagrange equation on the left-hand side is right here, and there's only one r dot dependence in the Lagrangian, so taking a time derivative of that, generalized momentum for the r coordinate, we get mu r double dot. And so our equation of motion for this system is mu r double dot is equal to mu r phi dot squared, okay? That's going to turn out to be the centrifugal acceleration, minus the partial with respect to r of the potential energy function. This is our equation of motion for the r coordinate.